All right, thanks everyone, and thanks for bearing with me. I'm actually dealing with an internet outage, so I'm doing this all through my data plan. So keep your fingers crossed that I can get through this. But my presentation is, I just put together a few slides on a small project I did to try to convince myself whether or not you could get anything useful out of Meteor colors. And of course, the motivation there is that we use color for a lot of things in astronomy. You can use it to probe a star's temperature, like I've illustrated here. There's evidence that color indicates the age of an asteroid's surface, and various other things as well. So it's very tempting to try and use this to look at meteors. Of course, the problem with meteors is that unlike the solar spectrum or asteroid reflectance spectrum, it doesn't have these broad features that vary in a predictable way. Instead, you have this very jagged type of spectrum that's heavily dominated by emission lines. So it's a real question whether or not you can do anything useful now with color to begin with. So I wanted to test this out in a very limited way. There's a catalog of meteor spectra published by Wojciech et al. In 2015, 84 different spectra, if I remember right. And they have already classified all of those spectra using Yuri Borowiczka and his co-authors' 2005 paper, The Approach there, where you classify them as, say, normal or an iron type meteoroid or sodium rich, etc., depending on the features that you see in the spectra. And here I've pulled out some examples from the catalog so that you can kind of see what those variations look like. Now, here it's the same set of spectra, but I've underlaid lines marking key emission lines. So you see a green line marking a magnesium emission line, yellow for sodium, and red for the oxygen 777 line, which is from heating of the atmosphere. And then there's also iron emission lines, but there's a bunch of those. So instead of putting a single line, I've got sort of a band there, a shaded region to indicate where the iron contributes. And so based on the relative strength of these, if you've got a full spectrum, you can say, oh, well, this meteor is rich in iron, or it's got more sodium than I might expect, and thus classify them into those different types. And so what I wanted to do is take these existing spectra, which have already been classified by somebody else. So, I'm not messing with that. And I wanted to see if I could, by feeding these spectra through typical color transfer functions and deriving synthetic meteor colors, whether I could successfully reproduce those classifications or not. So of course, I decided to use the Bessel, standard Bessel filter functions, BVR and I, which are shown here. And of course, those don't have a constant sensitivity within a range. It's a sort of function, which you have to then convolve with your meteor spectrum to try and derive color magnitudes. And so that's basically my approach. I take each of those spectra in the catalog, multiply them by the transfer functions, and get what you're looking at on the bottom plot here, which is basically a spectrum filtered through that color, which you can then integrate to get the color magnitude. And that's pretty much the approach in a nutshell, very, very simple. And then when you do that, you get this following scatter plot. So now there's a bunch of different colors you can produce. What I've selected here is B minus R, blue minus red, as a function of peak meteor magnitude. And the different color coding here within the plot is showing you the different spectra classifications. And what you'll notice mostly is that they're all pretty much piled on top of each other in B minus R. You'd be very hard pressed to tell the difference between a sodium-free meteoroid and a normal meteoroid using this metric. And I automatically generated all different possible color combinations, and that's basically true across the board. It's very difficult to separate these different spectral classifications on the basis of color. And this pretty much confirms what a bunch of previous studies have found, that it's very difficult to do anything with color. However, there was one possibly interesting feature, which is that you'll notice that those blue squares, the iron type meteoroids, do appear to be systematically bluer than the other meteoroids. And in fact, they're both bluer and less red on average compared to other meteoroids. So that when you use B-R specifically, they kind of stand out. So I hesitate to make this claim based on just 5 or 6 meteoroids here. But I think this is a potential avenue. If you wanted to do something with simple color bands, you may possibly be able to systematically separate the iron type meteoroids from the others. But that's apparently about all you can do with simple color bands. If you wanted to look at sodium or something, you would probably need more specialized filters or just do a full spectrum. And that's pretty much it for me, this short talk, and I can take questions.
Yeah, nice talk. Just a short remark.
Mm-hmm.
We tried similar things some years ago to distinguish between different showers. The idea was also that different intensity distributions in the spectrum, but the sample was too small, so we didn't end up with any real result, just as a comment.
Yeah, that seems to be a common finding, is it's very difficult to do anything with the color. Yeah, but thank you.